Hi, Roberto. Welcome back.
Hi, Robin. It's always a pleasure.
Third time now. So let's have a little intro to yourself and what's been going on recently.
All right. Like last time, I still work in ESA, the Philip, and I serve as an internal research fellow. So it's like a postdoc position. My domain of expertise is how to bring artificial intelligence on board satellites.
Hmm.
Lately, I've been working on a very specific topic, which concerns the automatic machine learning or AutoML.
Fantastic.
Um, what I've been working on is like how we can speed up the development of models to deploy it on our satellites in a more fast and efficient way. Because
Hmm.
there is always this kind of overhead in training your model, selecting your model, fine-tune it, deploy it on your satellite. Try to strike a good balance or a good trade-off between the accuracy of your model and the latency. So
Hmm.
how fast they can go.
Right. So on the satellite, you don't really obviously get to choose among different hardwares. They've selected something. You need to optimize your solution for what's already there.
Exactly, exactly. And you don't have all the power that you will have on the ground, right?
Right. Interesting.
You have a
So
lot of constraints.
yeah, I mean, could just ballpark, how would it compare on the ground? I've got my GPUs available in space. Are we talking about like 10% of the available compute, 5%, something like
Uh,
that?
so let's say on ground, you could have something like 300 watts of power.
Hmm.
On board, you can have something like 3 watts, but it strongly depends on how big is your satellite. For CubeSat, maybe
Right.
3 to 10 watts
Right.
of
So we're
power.
talking a couple of orders of magnitude in difference in available
Yes.
power, generally speaking. Very interesting. Right. So you have a paper that you've been working on. Let's cover some of the details.
Yeah, so I was questioning myself, okay, we always try to bring this model from literature when we need to solve a task. But most of these models that comes from literature, they have been hardly optimized on specific data set and some specific data distribution.
Mhm.
But when it comes to the satellite and to the new space segment, we're always looking at verticalized application. So I think like a satellite with onboard AI that generally has to do only one thing and it has to do it very, very quickly.
Mhm.
Like, I don't know, detect a wildfire here. So they have a segment with the constellation of these AI-enabled satellites, and they want to do only a single task. So
Mhm.
in that case, the model that we bring on orbit must be tailored and optimized towards that task and data distribution.
Mhm.
But we fail in do that because we usually take models already pre-made by the literature to solve very different problems, like I don't know, classification on ImageNet or object detection on COCO dataset,
Mhm.
which the data is completely different, and therefore their architecture is made for doing something completely different.
Mhm. Right. So you have a specific task, fire detection. You've curated a specific data set for that satellite, and the next optimization is curating the model.
Exactly, exactly. The thing is that you want to squeeze as much as you can the performance of that model and on that hardware that is available on your satellite because
Hmm.
you want to reduce the duty cycle. So you want to use as much as less power as you can. Because if you use
Hmm.
less power, you use less energy, of course, and the battery gets benefit from it. So you can extend
Right.
the lifetime of your mission. And so it's a lot of money that you can save in the end.
Yeah. So the best performance for the least possible power, that's the point you're trying to find.
So the point is that best performance for satellite application and this kind of a segment is not always having the best accuracy,
Right.
in my opinion. You don't want to have a model that performs 3, 4, 5 points of percentage at maximum. You don't want to have that delta increase if that costs you a lot of power on orbit.
Mm.
You want to strike a good balance between the accuracy, so how performant is your model in that sense, but also how fast that model is in processing the whole acquisition on your satellite.
Right. So we're not just talking about a metric that we're targeting now. We're talking at different kind of characteristics of a model that we want to achieve.
We can say that we are looking at a multi-objective optimization,
Right.
which we have two concurrent objectives and we try to optimize both of them.
Right. Okay. That segues nicely into how you're doing that with the architecture search?
So I've been looking a little bit, and I discovered that this kind of technology was already developed for computer vision tasks, but it was
Mm,
not really applied a lot in the geospatial community.
mhm.
So I decided to make my own framework. And yeah, what I did is like applying a genetic algorithm optimizer and like build this framework which is called PyNAS to that works in this way. Essentially, it creates population of networks, and then it just see which of these networks are the most top performing,
Mhm.
and then it further optimize the topology of those network in a cycle. But the
Right.
key part in this framework is that we profile each model on the specific edge device. So
Right.
we have similar devices to the one that are flying on the satellites,
Mhm.
and we see how these models are performing on these devices.
Okay, so you have on your desk literally these different computers plugged in, and you run your software, and you get scores for each of the different hardwares.
Exactly, exactly. So to expand a little bit on that, each vendor makes his memories on the device in a very different way. So you might find that some layers are better suited for some devices,
Mm.
or in some other devices, seems they use their own compilation. Some layers are not even supported, so you cannot use all the layers of modern deep learning on some devices.
Hmm.
So it's really a matter of finding what is the best solution for that kind of hardware that you have. It's
Hmm.
trying the software for your hardware. In
Interesting.
the yeah.
What are some of the sort of constraints there? What kind of layers are we talking about typically?
So for instance, in a Myriad 2 that is flying on a FISAT, on a FISAT 2, and was flying on Canini and FISAT 1, well, on that kind of device, vision transformers are not very well supported.
Hmm.
As I know, transformers are like kind of the basic block of the modern deep learning architectures.
Mm.
So these are like generally examples, but there are also other layers that are not supported.
Hmm.
Uh, in other cases, during compilation times, the kernel gets fused together. So um, sometimes, let's say, three convolution with a kernel of 3 by 3 works better than a single convolution with a kernel of 7 by 7, or
Mm.
vice versa for some other devices.
Hmm.
It's really it's really a challenge of discovering what is the best for your device.
Right. So for each device, you have a table which says these are the kind of optimized layers that you should utilize. Now design an architecture that utilizes them and gives me the best result.
Yeah, it works kind of like that, but I let the optimizer do all the job for me
Hmm.
by simply profiling each of these model on the devices. He is looking at which is the top architecture that is performing the best,
Right.
and then start like tweaking that architecture a little bit, discovering path, changing the topology, trying to see if that kind of architecture it can be improved.
Right.
That's this on in a parallel way, employing different models at the same time.
Right. I just want to understand the algorithm a little bit more there. So it starts with a kind of grid search, finds some promising architectures, and then experiments further on those, does it?
Yeah, no, this class of algorithm are known in literature as a meta-heuristic and are used to solve non-convex problem. This one in particular is a population-based, is the genetic algorithm.
Mm.
So you can consider it a grid. I see it more like a population. You have a population made of several different individuals, and each individual for you represents a model. And after each generation, you let's say you kill the worst performing, and then you
Mm.
recombine together the top performing, creating new architecture.
Hmm.
And the process continues in an iterative way
Hmm.
until you reach a top performing architecture.
Right. So you basically are watching these different models kind of rising
Yes.
up a ramp towards some kind of best solution and with the low performers being picked up.
Exactly. Actually, we at the end of this optimization, we obtain a set of top performing model, and one can cherry pick the model that best satisfies his trade-off. Maybe
Mm.
someone is more interested in having a little bit of more of accuracy. Maybe someone else for another device is interested in having a little bit more of latency.
Mm.
So at the end, you obtain this solution which has like the Pareto efficient solutions, and you can cherry pick the model based on your requirements.
Mm. So is there a lot of user skill required to get the best solution, or is it pretty much sort of push the button and it will arrive at the best solution?
Well, you can tweak a little bit the parameters, but more or less the optimizer should do the job for you.
Right,
You can change how big are these populations, so how many models you want to train at the same time,
right.
how much these models can be big, so how many layers, which layers they can use. You can tweak this, but on a general level, I would say that the optimizer really simplifies what you need to do
Mm.
because it does all the job in the back end, and you don't have to watch and to select which layers you need to use. It
Right.
does that for you.
Okay, so no transformers based on what's supported by the hardware. What kind of architectures did you arrive at for your different tasks?
Well, usually they are kind of similar to mix of ConvNeXt and ResNets or mobile in virtual bottlenecks, different kind of modules stack one on top of each other.
Hmm.
That's the kind of solution that he gets. But the remarkable thing is that these models are very, very tiny compared to the literature. We're talking
Hmm.
of a few thousands of parameters compared to
Mm.
multi-million parameters that you will find in a other model taken from another task for a computer vision problem.
Mm. And what's the sort of trade-off in performance look like there?
So for defining the trade-off, I used a mathematical formula. So I was basically combining two values in a single one, and that is the value that I try to optimize. It's
Hmm.
like having a sort of a weighted function that tries to balance both the accuracy and the latency of my task. And then at the end, I can see the results on these graphs, and then I can cherry pick which is like the model that mostly satisfies my constraints. That can be
Hmm.
different depending on the type of mission that I have or on the type of task that I need to satisfy.
Right, okay. So these results are presented in the paper. Um, Sounds very exciting. Which model is going to be deployed first then?
I think we have a lot of promising model here. We have a model for wildfire detection. This
Hmm.
is further described in the paper. We
Hmm.
also have a model for vessel detection that has been presented to a conference.
Mm. And I just want to have a look at the bigger picture here. So you have this model that's on the satellites making some detections. Maybe the accuracy has been traded a bit. Do they then integrate into some wider pipeline where other models are maybe looking at the images again on the ground, or is it just that single model that's going to do all of the work?
So, okay, you're touching a bit of a pain of a problem.
Right.
That's like the domain gap. Because usually we train models on a different data distribution on a different data set compared to the data that is actually sensed by this new space satellite. Because they
Right.
mount different sensors that are typically different from the data that we already have collected. And
Hmm.
so it's always like this problem on filling that gap because we
Hmm.
try, even with simulators, we try to simulate the kind of data that we expect from that satellite. But even in that case, there's still an existing gap between what we make synthetic, expecting
Hmm.
what the kind of sensor is acquiring, and what is actually acquiring on that satellite. So there is always this process of training one time, then you downlink again your images, and then you fine tune again your images, your model on these new images. This
Hmm.
is I will not say it's a continual learning process, but we try to fine tune to tweak the performance, and we need to
Hmm.
re-update the model in most of the cases. This is something that happened in the past, and I will say that having models that are very small is an advantage
Hmm.
because it's kind of easy to fine tune it, and it's kind of easy to update again these models because their weight in terms of megabytes is very very low. We're talking
Hmm.
about megabytes of models, or sometimes even more, even less.
Hmm.
It's kind of
Interesting.
easy to uplink.
So you anticipate updating the models in response to gathering more data, of course. Um, and also, how practical is it to deploy these models? If you want to deploy a new version, is it kind of a straightforward deployment, like CI/CD kind of operation, or is there a lot of work to sort of get data and model ready for going on a satellite?
I would say most of the work here is mostly on the data side. It's
Hmm.
not really on the model side because these pipeline here are just bit. They're not really in CI/CD, but they are kind of like optimized and automatized. So
Mm,
I say there is not too much of work on that. But on data side, you really have to make a pipeline for your new data, and
mm.
then you need to update that model because mostly of this data is not labeled. So you really have to bear that in mind.
Right, okay. So there'll be a period where you're basically onboarding this model and, viewing the predictions maybe and some adding some more data to the training data set and potentially tweaking the architecture a bit and kind of going around this loop a few times until you're happy.
That's something that usually happens. Maybe not tweaking again the architecture, but it really depends. But at least that giving a bit of fine tuning on this new data.
Right.
Sometimes it's not necessary to have a lot of this data. You can do a small fine tuning on only some very good quality information,
Hmm.
but you still have to know that there is this gap and you need to close it.
Right. Of course. Moving on to the actual hardware that's available, what are the brands and what do the performance look like of those hardwares?
So, okay, um, we have, of course, Nvidia with the Jetson chipset. We have the Myriad from Intel
Hmm.
and some of the boards developed by Robotica. And we have some boards developed from KP Labs as well. I hope to not forget someone, but I think I'm gonna forget someone. But
Hmm.
still, there's a lot of hardware and there's a lot of push on this kind of processing unit that can do
Hmm.
accelerators for small satellites.
Right, very interesting. And do these different providers, do they take different approaches or target different kind of applications?
Let's say that they are very different one from each other.
Hmm.
Also in the way they work from a model during the compilation time.
Hmm.
And that regards again the problem that we were referring at the beginning, that not each layer is supported by each one of those hardware.
Right, okay. I'm curious if there'd be a feedback loop that you would basically discover certain classes of models were optimal for certain kinds of tasks, and that would drive you towards particular hardware and give an edge to
Well,
one provider.
it's very difficult to extrapolate this generic rule because it also depends in the way you make your optimization. In the sense that if you look at the paper, you will notice that the models trained for the myriad were much strongly optimized towards the latency. That is coming from a physical problem that the myriad is a very low power device.
Hmm.
So when you set that function to optimize this fitness between accuracy and latency, this is strongly pushing towards the latency compared to the accuracy.
Interesting. And so a different provider might head in a different direction, sort of utilize more power, but be targeting a different kind of task.
I would say that the NVIDIA hardware is more general purpose and in particular is more powerful.
Hmm.
Uh, Intel devices are much more focused towards certain kind of layers that are a bit more efficient and they
Hmm.
use much less power consumption that this NVIDIA chipset that we have right now. But we are also in an historical period where things change very, very quickly. New hardware gets updated and new satellite gets launched every 6 months. I know for
Mm.
sure that next year we're gonna have new mission like IX. There is also a constellation of AI-enabled satellite by planet. It's the
Hmm.
Owl constellation. So um, I think that the things gonna change quickly in the future, but there is something that will be always constant in each one of these missions. That is the uh, efficient optimization of the models for a specific hardware. That is something that you cannot overlook. You need, of course, to use as much less power as you need because this is going to extend the lifetime of your mission.
Hmm. Fantastic. Well, really interesting topic. Congratulations on the paper. That's already published or that's to be released soon.
Published, it's open source, the code is available, the data sets are all freely available.
Hmm.
But in case you have any doubts, I ask you to connect with me. Just send me an email or a message on LinkedIn. I will be happy to provide with more information.
Brilliant. I'll drop all the details in the show notes. Well, once again, thank you for joining me and all the best with the deployments, and let's catch up again in the future.
Ciao, bye bye. Thank you.
Ciao.